We're going to look at something that's related to the chain rule, which is called implicit differentiation. And the idea here is that sometimes there are really nice relations that we'd like to be able to find derivatives of, but they aren't functions. Just take, for example, x squared plus y squared is 25. You guys all know that one. What is that the equation of? What is the graph of that equation? It's a circle. We'd like to be able to find the slope at any point we want to on that. Problem is that it's not in function notation. So we'd like to be able to not have to try and write it as a function first and then find the derivative. And the process for doing that is implicit differentiation. So start off with an idea here. The derivative with respect to x of x to the fifth is not the same thing as the derivative with respect to x of y to the fifth. And you're like, okay, yeah, I know that. But you may not grasp the subtlety here. The derivative with respect to x of x to the fifth is 5x to the fourth, right? Notice that what we're taking the derivative with respect to and the variable match one another. But in this one, the derivative we're taking the variable that we're taking the derivative with respect to doesn't match this variable. So what we're going to do is we're going to treat y as an unknown function of x and then use the chain rule. So if y is equal to f of x, remember dy dx is f prime of x. So we don't usually take the time to do all of this, but here's what the idea is. If we're taking the derivative with respect to x of y to the fifth, that's the derivative with respect to x of some unknown function of x raised to the fifth power. Then we apply the chain rule. We have 5 times f of x raised to the fourth. Remember, take the derivative of the outside part, leave the inside part alone, times the derivative of the inside part. And then substituting back in the y's and the dy dx's, you get 5y to the fourth times dy dx. Now, it is a pain in the tuchus to have to do all those steps. So implicit differentiation allows us to go straight from this to this without having to do all that substituting and unsubstituting. But that's the basic idea. So when the derivative or the variable that you're taking the derivative with respect to doesn't match the variable that you have, what we're going to do is take the derivative as normal and then use the chain rule, multiply times the derivative of that inside part with respect to the variable you're taking the derivative with respect to. Yeah, I know, that was a convoluted sentence, but I think you got it. So, for example, if you're taking the derivative with respect to x of 3y to the seventh, well, you start off just as normal. That'll be 21y to the sixth. But again, since these two variables don't match, we'll have to multiply times the derivative of the inside part. The inside part is the y. So we're going to take the derivative of the y with respect to x, that is dy dx. If we have the derivative with respect to x of a product, a sum like this, we'll just do each individual term. So what's the derivative with respect to x of 4x? 4. No big deal, right? Then the derivative with respect to x of y to the third, we start off just as normal, 3y squared, but we have to multiply times the derivative of y with respect to x because we have to respect the chain rule there. If you have a product, you should use the product rule. So if I have the derivative with respect to x of y squared, I start off with the first factor, x, times the derivative of the second factor, which will be 2y, times, again, the inside part is not x, so times dy dx, plus y squared times the derivative of x, which is just 1. And then we'll usually take the time to rewrite that as 2xy dy dx plus y squared. Now, here's what's going to happen. Almost always, you're going to start with the equation of some relation. And then we're going to take the derivative with respect to x and then solve for dy dx. So, for example here, find dy dx for this horrible, with the x squared plus y squared equals 25 example for a circle I gave you a little while ago. You can break that into two different functions and it works fine. It's kind of a pain, but you could do it. Here, I don't have a clue as to how you could solve this for y. I'm not sure it's even possible. But what we're going to do, and we usually don't take the time to write this, but I am for the first couple of examples, we're going to take the derivative with respect to x on both sides of the equation. So for the y to the fourth, that'll be 4y to the third times, because we have to use the chain rule on this, dy dx. Plus, I'll keep the first factor, x cubed, times the derivative of the second factor, which will be 5y to the fourth times dy dx. Plus y to the fifth times the derivative of x cubed, which is just 3x squared, minus the derivative with respect to x of x to the seventh is just using the power rule, that's 7x to the sixth, equals the derivative with respect to any variable of a constant is 0. So now what I will do, and I'm going to do these two steps at once, anything with a dy dx in it, I'm going to keep over here and clean it up. Anything without, I'm going to move it to the other side of the equation. So this is going to be dy dx times, I've got a 4y cubed plus 5x cubed y to the fourth equals 7x to the sixth minus 3x squared y to the fifth. And then we'll simply divide. Dy dx will be 7x to the sixth minus 3x squared y to the fifth over 4y cubed plus 5x cubed y to the fourth.
That was one problem.
Yeah, yeah, that's one problem. I did try to get to some of the worst ones quickly. All right, page 2.
Yeah, it usually gets harder as you go on.
Wow, there's only one thing on page 2? Oh, and the other pages, okay. The other pages are like Monday's lesson.
So this is Monday's?
Well, pages 3 and 4, where it says continued, I think that's Monday's lesson.
Okay. So we have one page to determine the slope.
Well, I don't think it'll take all of that.
Oh.
Hope not.
It's like the worst. When you get to like the back of the test, and it's like the longest problem I've ever seen.
Yeah. All right, so determine the slope of this ugly hose beast at the point 3, 1. This is about as ugly as it gets. Okay? So, we're going to take the derivative with respect to x on both sides. So, on the left side, starting with the outer part, that'll be 6 times x squared plus y squared to the first times the derivative of x squared plus y squared with respect to x. So for the x squared, that's 2x. For the y squared, that'll be 2y times dy dx. Equals, when I have something like this, I think I've mentioned it before when you had to use the product rule. I think of it as 100x times y instead of 100 times x times y. If you think of it as 100 times x times y, then you have to remember to distribute the 100 at the end of your work. If you do it this way, it's just a straight product rule. So I'll have 100x times the derivative of y with respect to x, which is dy dx, plus y times the derivative of 100x with respect to x is 100. Now, here's the important thing to keep in mind on this. They didn't ask you to solve for dy dx and then substitute in the 3, 1. They just said find the slope. So the slope is dy dx when x is 3 and x is 1. It is, especially on this one, I picked this one out because it's ugly. Trying to solve this for dy dx, you've got to distribute all this inside of this, bring this over. I mean, it is ugly. But if you go ahead and substitute in 3 for x and 1 for y, it gets a lot nicer, a lot faster. So when you're doing one where you're actually looking for a slope by substituting in the coordinates of a point, take the derivative and don't try to simplify it algebraically first. Go ahead and substitute in. So when I substitute in 3 for x and 1 for y, let's see, that's going to be 9 plus 1 is 10, so that's 60. Times 6 plus 2 dy dx equals 300 dy dx plus 100. That's a lot nicer than it would have been otherwise. I will still need to distribute, but this will be 360 plus 120 dy dx is equal to 300 dy dx plus 100. I'm going to subtract 120 dy dx from both sides. That's 180 dy dx. And subtract 100 from both sides, so that's going to be equal to what, 260? So dividing both sides by 180, we've got 260 over 180 is dy dx. So what, 13/9? So the slope is about 1.5 at that point. Now, just so you can see this graph, first of all, your calculator, not so much. It won't do these sorts of graphs. It doesn't graph relations. It's one of the things that is a limitation to the TIs. Some of the Casios and the like, some of them will graph relations like this. A TI absolutely will not. Equals 100 XY. Yeah, yeah, I would have guessed that. Never in a million years. All right, and we know that this goes through the point 3,1 with the tangent line having a slope of 13/9. So, just so I can write this out, that would mean that y is equal to 1 plus 13/9 times x minus 3. You don't need to write that down. That's just what the tangent line would look like. So if I graph that, y equals 1 plus 13/9 parentheses x minus 3. Boy, I hope I got it right. Oh, look at that. You got to admit, that does look pretty nice.
It makes me happy that we got it right.
You think it makes you happy? When I do one of these and I'm like, so let's look at what this looks like, and it's like, uh-oh. I've had that happen more than once. Yeah, I'm like, okay. Yeah, it usually goes to the right point, but I'm like with a completely wrong slope, and you have to go back and figure out what went wrong. Yeah. Okay. Questions? Okay.